means that it's exteroceptive, and but also those are passive. That you external object has to push a switch, push a bumper to have a reaction. We have an optical barriers. You can see they are active because they emit light and they detect when the beam of light is blocked, and then they measure then some object is crossing this barrier. Then proximity sensors that measure, that detect there are objects close to the robot. They can be passive or active. Those are different technology. They can be resistive, inductive, and so on. Also measuring the external connections. Then we can have haptic sensors. Haptics means that we are trying to perceive the force applied from the external source. So not only just a fact of being of touching, as we have in the first group, but also the value of this touch. So we can have like contact arrays that detect distribution of the force on some area. Force and torque sensors. We can also have resistive haptic devices. In fact, I guess one of the projects is also using that for haptic paddle that I hope you will see somewhere at the end of the project. Then, as you can see, there's quite a lot of motor axis sensors that we can get. They are only motors are inside, so most of them are proprioceptive, so measuring the internal state of the motors. We can have the encoders of different type with Bruch encoders, optical, magnetic, inductive, capacitive. We can have potentiometers or resolvers that can also give an information about the position of the and sometimes velocity of the either a motor or a rotating axis. We can also have the heading sensors for the direction where the robot is, what is the orientation of the robot. Again, compass, gyroscopes, inclinometers. Then the sensors that are measuring the position of the robot with respect to certain beacons. Beacons are the sources of some emissions. So, for example, like in GPS, you have the satellites that emit a signal. The robot receives the signal. The main assumption in this method is that you have several beacons that send some data, and based on either a difference in time of receiving the information or by a knowledge where the beacons are, you can get the information where the robot is. Okay, we'll not explain it in details of how it exactly works, but just what you need to know that there are some points away from the robot that are actively sending some signals received by the robot. Okay, then you can have ranging sensors, again working on the different rules, and you can also think that they are quite similar to the proximity sensor, but when you say about proximity sensor, we say only about a binary output of there is an object or there is no object. So that's it's like working like a detector, yes or no. When we say about ranging, we get the information about the distance. And yeah, lots of different options: capacitive, magnetic, sonar, camera, laser ranger, structure light base. So yeah, different approaches. When we go later to the vision-based sensors, we will also say about how the ranging using the vision system, so the cameras or structure light, how they really work. Then velocity and motion, Doppler radar, Doppler sound sensor, camera, accelerometer, and the identification. So to recognize certain, quite often biometric, but not only. We have camera, RFID, laser ranging radar, ultrasound, and the regular sounds hearing. Okay, so that's just a very quick overview of all the types of the sensors. As I said, it's good to know the terms. So if you are not familiar with any of them, just please check what it is. I suppose that you know most of them, and more or less know how they operate. So I hope it's clear. Maybe if you would like to hear about some of type of the sensors a little bit more, we can return it at the end when we after these next lectures about the proximity sensors and the vision. Maybe some others also you would like to hear how they work. So please just let me know. Okay. So what we get further. So when we already have the data, we can try to transform them. So the filtering, the standard like averaging filters and median filters, you probably know. But then we come to the methods of estimations, and again, we will not say. We will not explain the details of the methods. You probably already heard about them in some other courses, or you will hear about them. Just to recall the names in the context where that they can really be used here. So you have the least square method estimation. You have maximum likelihood estimation that is quite similar, but uses the probability distribution parameters. Then you have maximum a posteriori probability. That's again some statistical technique. Minimum mean square error. Again, probabilistic method, Kalman filter. I'm not sure if you heard. I think. Okay, probably you've heard about it. I don't know how many, how much into details you were explained. So those are for linear systems. For general systems, when they are nonlinear, so you can either use linearization first and some elements that use the linearization, like extended Kalman filter. You can have particle filtering, which is an example of sequential data estimation. So you just make some randomization of the particles and then average it. That's the method also known as Monte Carlo. So if someone of you have heard about it, that's the Monte Carlo method. And then you can have some graphical models like Bayes nets or neural nets, or you can have the algorithm based on voting. So you just they basically work in the way that you have lots of data and you want to get some information out of it. So you just, to simplify the process, you just select some subsets of this data, make some estimation from these subsets, and then compare the results and saying, okay, which of the results is the best of what we got. Yeah, that's kind of the voting. Yes, how many points fits to a solution that is somehow simplified. And of course, a note at the bottom. Okay, those are names that you could hear about them. They are quite often used, but of course it's not everything. There are many more methods, and all the time there are new methods appearing. So it's not a complete list, yes. But anyway, it's worth to know about these methods that are mentioned here, because those are quite often the first tries. Yeah, so you get the data, you cannot use the raw data that you received. You need to do something with them. So those are usually the methods of the first try. Okay, people just use yeah, the least square is like the simplest one. If it doesn't work, we go to something complex like Kalman filter. And only if it doesn't work, even with the more complex elements, then they go into start to analyze and make a dedicated method, a completely different one. Those are kind of the standard approaches. Okay, and those were the estimations, but then we also said about the data associations. So after you already, what is the difference? Estimation is supposed to remove the noise, remove all the errors that could appear. So the regular noise, some outliers that are not fitting to the process, something that was not, some special events that you want to eliminate from the process. So those are, in general, you can call it filtering, although it's a little bit more than simply a filtering. And data association is like trying to get some more general conclusions from the data. So, for example, you get a point and you say, okay, let's try to classify it into a certain group. So the methods that you get is like k-means and k-nearest neighbors. I hope you have heard about them. Those are just the most common approaches. Were they somewhere explained or not? No answer. Neither yes, no, not, nor no. Okay, so generally the idea in clustering is you have certain classes of objects and you have a lot of samples. And if you don't have an, let's say, rigid algorithm to process, to say, okay, the certain features of the sample say that it belongs to this class. Instead, you can use the method of, okay, we have hundreds of examples from class 1. Let's say we have 100 of images of a table, and we have 100 of images of chairs, and we have an image of an object, and you want to decide if it's a chair or a table. And you can do just comparing comparing a current sample, current image to the image that you had before. K nearest neighbors means that, okay, you try to find the, let's say, one nearest neighbor. Method would be like, okay, let's find the image that is most similar to what I have, and let's assume that the object that we are now getting is of the same class as the object from the class that we already know. So the basic approach. K nearest neighbors is just a voting method. So you can say, okay, let's take 5 nearest images to this to the current one, and let's see. And when we find these five other images, we say how many of them belong to class A. So how many of them represent the table, how many represent the chair, and the bigger number is the class of the image that we are asking about. So that's the nearest neighbor approach. K-means is that instead of comparing to the nearest neighbor, you compare to the average of the other samples. Expectation maximization, that's a method that requires some representation, not with particles, but with distribution. And again, it's just, you just integrate and use the expected value in a sense. Again, not explanation here, just get to the course of statistics, statistical processing, or data identification where they should appear. Those are clustering in space, but also you can cluster elements in time series. So you can use the methods of self-organizing maps, hidden Markov models, support vector machines, which are used to represent the data that change in time. And for example, you want to recognize the objects. Okay, is the object moving in this direction or other direction? When it stops moving in that direction, or when it stops, let's say, when you observe a person and you want to know where the person stops doing certain activity, you can analyze it based on this time series. So you just try to divide the images that you get, the video that you get from the observing activity of the person. You could try to split it, for example, for single basic activities one by one. Okay, and again, the note is the same as if previous. Okay, those are the standard approaches, the most common, but not the only ones. You can also find the others. Okay, so those are the general classifications part, and what to be taken and remembered later when we are these questions of firstly, how to classify the sensors, what are the main types and what they really measure, and how to process the data after acquisition. So what are the stages of this processing the data when they are already taken from the sensor. Okay, so let's finish with the general part and let's go to the more details of encoders and time of flight ranging. So firstly, when we talk about the encoders, so those are the sensors that transform the mechanical position or motion to electrical signal. And what types of the encoders we can have? We can measure the motion that is either linear or angular. We can get the output that is absolute or incremental, and we can do it with a different technology. So they can be mechanical, optical, magnetic, or capacitive encoders. And you can find almost all combinations, and of course in many possible devices that you get. Just two examples you can see to the right. One is the linear encoder. As you can guess, you measure the movement along the line. Then is the rotational encoder, the angular one that measures the angle. What does it mean that the output is absolute or incremental? The absolute measurement means that whatever place you are, you just know exact position. So let's say that each part of this has a certain code. Let's call it a code that says, okay, when we are in that point, we make a measurement and we know exactly that we are in this point. The incremental encoders are the encoders that measure only the change of the value. So when you are in certain points and you don't know where you were a while ago, you only know how much you shifted from the previous step, but not what is the absolute value of that. So usually with the incremental encoders, you need to either reset them in certain position, go to a limit, and start counting again, or you need to store the previous value somehow. For example, in Fanuc robots that we have in laboratory, the data from encoders are stored in memory. So even if you switch off the robot and turn it on, the values are read from the memory of where the robot should start counting its position again. As about technology, so you can just guess of what physical properties are used to get the information in each case. So we'll show the examples in a while of different approaches. So firstly, you can see the absolute encoder, and this is the kind of that is the optical absolute encoder for the rotational. So you have certain axis that is rotating here. At the end of the axis, you have the plate, which has a certain certain markings. The markings are either the holes in these plates, or those are elements that are either transparent or opaque. And generally, as you could see, you can see that you have some light emission here. You have a phototransistor on the other side, and you can see that you have the codes on the plate. And based on these codes, you get certain readings, if it's white or black, for each line, for each diode transmitting the light. You get a corresponding information, and you can, based on it, you can decide at which angle you are now rotated. It is very useful. Of course, these absolute measurements counts only until the full rotation. Yes, so if you make a full turn, you are again in the same position as you were at the beginning, and you need to deal somehow with it if you want to know know the angle more than one full rotation. Okay, the disadvantage of this method is that the precision of the encoder is exactly defined by the number of the lines that you have here. So if you have like 8 lines in here, it means that you can divide the plate in 256 different positions, so the precision of the orientation will be less than 1 degree. Then if you add additional two diodes, you will have more than 1,000 in different possible values. So you will have like, okay, 1/3 of the degree, roughly, the precision. So that's the way of complications. You can imagine that, okay, if we want to have a higher precision, we need to have a bigger plate, and all the encoder will be bigger as well. It is the absolute version of the rotary. You can find two different types of the plates. One is the binary code, and second is the gray code type. Does someone know of why? What is the advantage of gray code with respect to binary code? What is the special feature of using the gray code here?
Like we are avoiding some bit flips errors?
Yeah,
because
exactly.
with increment, only 1 bit changes.
Yeah, exactly. That gray code causes that in each changes, when we go each step to the, let's say we rotate to the right and we go from one position to the next position, only 1 bit changes at the same time. What is the problem? The problem is that if you have, for example, a position in here, the binary, so you get, if I find it somewhere. So let's say that you go on one point, you go like this, and on the second you go in this one. You have 2 bit changes at the same time. And if you have a problem with a sampling, and you are sampling usually with a microcontroller, you don't really get the data in exactly the same time. You are probably reading either first and the second, or the second and the first, and it may happen that one of them has not switched yet, and the second one already switched, and so on. So that's the problem that appears in the binary code. But great, you know that. One more thing, if you think about the linear encoder of that type, it's simply the same code, but put on the line, not on the rotor. So you have the same features. Again, you can use the binary code or gray code, and yeah, just on a straight lines. Okay, when you have the incremental encoders, then you have a different approach, because you can have, in fact, a single channel, dual channel, or dual with Z channel. And what does it mean? The single channel is that the encoder that you have, okay, you have just holes in the plates, and you have just one diode and one transistor receiving the data. You can measure the velocity then, but you cannot detect, for example, the direction of the rotation. So you can count impulses, but you don't know if it's rotating left or right. If you have the 2-channel input, the 2-channel input usually means that the input is shifted a little bit. So you have like these diodes are a little bit shifted with respect to each other, and so they are not on the same radius. So it means that you can detect which of the diodes that of the transistor, in fact, that detects the data earlier. So you know which direction of the movement is, and then you can know if you want to add an increment or subtract it, and if you have the special arrangement with the half phase shift, you have something like a quadratic encoder. So in fact, you get you can in processing you can get additional 2 bits of the precision by simply analyzing the four subphases. Yes, so when is one is on, second is off, 2 on, and so on. So during the one phase between one first and the second impulse from the second tick, you can divide it into 4, so getting 4 times more higher precision of the measurements. The Z channel, as you could see, is like an additional input that appears less often, usually 1 for a turn. So you can count also the turns, and you can also use this channel for resetting the count when it's needed. So you know it's like kind of the 0 position for the encoder. And yeah, when you go to the laboratory and want to see it, that's exactly the solution from the that is used in FANUC in the yellow robots. When you lose the calibration of the robot, the process is you need to roughly put the joints of the robot in a indicated position, the position indicated by arrows, and then the robot automatically search for the nearest 0 close to this point, and then it calibrates itself correctly. Okay, so those are the encoders. How the quadrature encoder works, I think you probably know, and you can just look at the example that is given in the link that probably explains it best of what's going on. Okay, I think we have almost done it, so we can just skip the exercise. But the second part, I would like you to think for a while and try to give an answer, maybe in a chat, of what you can get. So we have an incremental encoder with two channel type with 500 pulses per revolution, and we put this encoder on a motor that makes 12,000 revolutions per minute. So how quickly you should measure the data to make a correct measurements with a microcontroller? Yeah, just let's say 5 minutes for a quick calculations training, and to see what the problem may be. Okay, if someone doesn't want to go in the numbers, you can just say how how to calculate it, what is the method of calculating the data, how to deal with these numbers, let's say, using the words, what we need to do. Yeah, okay, yeah, that's exactly the answer. Just to say of how to take these values. So you need to know how many impulses per second you have. To take impulses per second, you need to get the number of revolutions per minute, then take the pulses per revolution, and okay, that much you get, or yeah, and when you already know the number of impulses, you just get, okay, you need a proper frequency of your procedure to get it. And yeah, that's the timer that is 17 bits. And if you want to do it by your own procedure, because sometimes some people use directly the inputs of the microcontroller, then you need to have all the procedure that needs to be finished in, yeah, that will be 10 microseconds, very, very short time. Is it a realistic case? Okay, maybe it's not a common incremental encoder. Usually you use a smaller value here, but quite often there are motors with higher rotational velocity that are used even accessible in a normal usage. For example, for those who fly the drones, they know that it's like 2 or 3 times, can be 2 or 3 times more than it's here. Okay, so that's the kind of the problem that you usually need to deal. So that, and it's in fact just an example of what kind of the engineering problems you are needing to solve when you build a system. So it's not only you take a device, you say, okay, the device is fitting somehow to our needs, it has a proper range, but then you need also to think, okay, so we get that amount of the data per second, and then we need to do something with this data on the microcontroller side or a computer side, depending on what kind of the system it is. And then you need to calculate the capabilities. And then you say, okay, but if we want to control, let's say, 5 motors at the same time, it can start to be difficult. Similar thing may happen when you use the vision system. That's the main problem, is also the bandwidth that the data that you are receiving. So every stream from the camera is few megabytes, or even more if it's a high resolution. And if you want to connect like 2 or 3 cameras, then you need to have a capabilities of even transferring this data through the to the computer that you have. If you want to store it, it's also a problem of the bandwidth of the disk that you have, and so on. So those are also the things that you need to remember. It's not only the sensor side, but also the other place where you connect it. You also need to think about the amount of the data received and the timing that you also need to care of. Okay. Okay, the other part is just a special. We can just skip it right now. Okay, so when we have the magnetic encoders, they work in a similar way. So there are some there's a linear magnet with the north and south polarization interchanging, as you can see in here, and just sliding along this line, you just get the proper impulses. And the first example is just a pure incremental. The second one is incremental with resetting every sometime, so like a reference points, similar to the Z channel of the rotary encoder that we have seen a while ago. Then you can have a special approach for semi-absolute reference. So you can have this reference points that you can see that there are 2 reference points in different distances. So there is a different distance here, here, and here. So you know that there are 2 reference points close to each other, but depending on their distance, you can also determine exactly the absolute position where you are. And a similar approach is with the continuous. So as you can see, those are really different industrial approaches to the magnetic linear encoders. All options is just from what you can really get from different companies, depending on what are your needs. And of course, what you get is on the reading part, you just receive the magnetic field, you measure the magnetic field, and you just you can detect how the magnetic field changes. Okay, the advantage here is that in fact during the movement the change is continuous. So between the 2 different polarization, the change is continuous. So in fact you don't have a sharp on-off option as you had in an optical encoder. Here you have you can also have a bit higher precision resulting from the continuous change of the magnetic field in that point. Then you can have a capacitive encoders, quite interesting, probably the newest solution that appears, that you can find it in the rotary encoders, and those are simply the let's say the capacitors with a changing capacity. The capacity depends on the you could see that those are printed tracks of different shapes that cause that the rotation of the middle the middle part causes a different capacity of the whole structure, and the change of the capacity can be interpreted as a precise absolute angle of the rotation. So that's quite an interesting solution, especially from the because this middle rotor can be this predict can be customized to any need. So if you want, so it doesn't need to have the constant precision along all the full range of angles. You can prepare it for the range. You can change the precision depending of the angles that you are interested in, especially, and you can decrease the precision in other places just by making different shapes of this printing in the middle, so that can be customized. And yeah, those are it's one of the idea. Another approach that you can find is that the element in the middle is not printed; it is just shaped to the special shape. But the idea of how it works is exactly the same. Okay, and when we say about the comparison of these encoders, you can have these three types: capacitive, optical, and magnetic, and different properties that influence the applications, so such as resistant to some environmental conditions like dirt, dust, or oil, accuracy, temperature range, current consumption, programmability, package, how big they are, if they are immune to EMC, if they are immune to magnetic field, and what resolution you can get. So just to see that you can find advantages of each of the solution in depending on the needs that you have. That's kind of the part of this engineering work, to select of what is really the best option for the exact system that you want to build. Okay, so those were the encoders, most measuring the position and sometimes also velocity. And then the second part, the time of flight ranging. Measuring a distance based on sending some energy, so sending some signal, then waiting for the signal to return back, and time, as the name of the method indicates, it's time of the flight. You measure the time when you send the signal, when you receive the signal, and based on the difference of the time and the propagation of the sent signal, you just calculate the distance. So basically you do something like that. So time of receiving minus time of sending divided by 2, because you go there and back, multiply by velocity, and that's the distance. That's returning to what I said at the beginning. So you want to know and measure the distance, but in fact you are measuring the time so it's not exactly the same value, and we will say about the problem that it may cause. And what kind of the waves we can have? So we can have ultrasonic, optical, or radio. Depending of which type of the signal you use, you will have a different velocity in that place, but also you will have a different conditions of propagation of that different waves. So let's make some brief exercise again with some calculations. So we can use the two different time of flight ranges, ultrasonic and electromagnetic. And let's say that we have an object that is 3 meters away from our sensor. And can you say what is the minimum time of the measurement that we will have, and what is the resolution needed if we want to have a 10 millimeter precision of the data? Just to recall, because probably you will need the formula. So the formula we had, that was the distance, was the, let's say, delta time over 2 times the velocity. So when we use the ultrasound signal, what is the velocity of that signal? Roughly, someone remembers? Yeah, something like that. Just to simplify, it's 330, but let's say it will be 300, so 3 times 10 square meters per second. Then it will be easier to use this, to cancel this 3 that we have indeed. And with electromagnetic, so like light or laser light that you are sending, okay, that's in a while. So what will be the minimum time of the measurements? So how much it will take to measure the distance to the object? For the ultrasound sensor. Yeah, exactly. So we have like 20 milliseconds of the measurements. 20. Just checking. Okay. And if we want to have a 1 centimeter precision, Okay, so how was the 20 millimeters, 20 milliseconds received? So we just take inverse this formula, taking that what is the delta t when we know that the distance is 3 meters and the velocity is 300 meters per second. Yeah, and that's how we get this time of the measurements. And when we get, yeah, it should be even more than 1 kilohertz. Why? Because we need to take, in fact, this change of the distance. We can take like 1 centimeter. So using the same inverse of the formula, you may know how small time causes the difference of one centimeter switch. So it will be like so what we get, we have like 0.01, so that's our 1 centimeter. We have this delta time, we have 2, and we have again 3 times 10 to 7. So well, let's put it like 10 to minus 2. So in total, when we transform it to our delta t, it will be like 2/3 of 10 to minus 4. Yes, so it is even higher frequency than 1 kilohertz. Okay, and what will happen with electromagnetic measurements? The same questions, but what changes for electromagnetic for laser ranging? That's the velocity. The velocity goes few thousands times higher. So it means that the times that needs to be measured go even low, and the frequency goes even very low. Maybe I will leave it to you for the calculations of how it is. What are the real needs for the laser ranger to precisely measure with 1 millimeter precision, and why it is a problem with time of flight measurements. And let's go further to finish on time. So you can see just the examples of different ultrasonic rangefinders. The top are the industrial versions with different externals depending of whether they are resistant to certain industrial conditions or not. At the bottom, you can find the amateur versions from the very cheap, the basic SR04, to a little bit more expensive with the pre-processing on the microcontroller on a board from Max Sonar. The two at the bottom are quite commonly used in different amateur mobile robot constructions. So what we have in ultrasonic sensors. Usually the beam is sent. You send the beam of the frequency between 40 and 108 hertz, no, kilohertz, and if you reduce the frequency, you get a longer range. If you have a higher frequency, you have a shorter range. But the shape of the wave that you are sending can allow increasing the precision. It can be the ultrasonic rangers can use either piezo or electrostatic transducers. Piezo transducers are have a shorter delay and shorter time of stabilization. So when you send a command to send a signal, you faster get the signal transmitted. With electrostatic, it takes a longer, so you cannot measure with the very high frequency. Okay, you have the basic formula for the speed of sound in the air, and as you could see, they are dependent on, firstly, on the temperature, but also on some ratio depending on pressure and humidity. So yeah, the basic velocity is for average conditions, like 330 meters per second. But if any parameter changes, then in fact the sound velocity also will change. And you can also see, let's return to this, you can have sonars that work either in switching the mode between transmitter and receiver, and you can have a separate transmitter and receiver, as you can see at the bottom left. So the bottom left is that one module sends the signal, and from the very beginning, the second one waiting for the reply, for the signal arriving. To the right, in max sonar, it is the same module, works both as transmitter and receiver, so it transmits a wave, and after transmitting, it switches to the receiving mode and then receives. Of course, it is a simpler construction with a dual mode, but the main problem with this solution is that you get certain dead zone in front of the sensor, because if the object is too close, the wave that you were sending will already reflect and return before the module switches to the other mode. So that's why usually the single, so the dual mode sonars, they have certain minimum distance of measurement, and they cannot measure something below that. What we get in these ultrasonic sensors, in those which are used in robotics, those are the sensors between 10 centimeters and 5 meters, and the resolution that you get is about 1 centimeter. What is important also to know is that the beam is transmitted in certain, not in a single direction, but with certain angles. And as you could see, this is the so-called measurement cone that represents the energy sent in different direction. So in the direction when the sensor is oriented, you get the higher energy, but also, let's say, until these values, which is like 20 degrees angle, the energy is quite high. So in fact, everything that is in this cone, any object that appears here will be detected when it reflects. So not only in the center of the beam, but also to the sides. But also you can also get the reflections from the even from the sides of here. But of course, the reflection will be much smaller. So it would need an object to be closer. What we need to remember also from the physics is that the energy of the beam decreases with the distance. So that's why you get the maximum range of the sonar sensor, because it requires certain amount of the energy to return back to be noticed by the sensor. So the farther is the object, the less energy will return and the detection will be smaller. But you can imagine that it's the same problem here. So you emit some energy to the side, and if the object is close, then it can reflect also from the side. So it is not very precise in the sense of the direction. So you can get quite precise measurement of the distance, but you usually do not know the exact direction where the object is. Does it have a usage? Of course, yes. And as you probably know, lots of cars have parking sensors using the sonars, exactly because of this not precise direction, because you really do not need to know exactly where is the pole or where there is a wall behind the car. You just need to know the distance, and the exact direction is not so important. So that's why these sensors were used. Also, their advantage is they are quite cheap and not so complicated to use. In robotics, disadvantage that appears is that the measurement is quite long. So if you want to measure in different locations with multiple sonars, as you could see, when you have an object 3 meters away, you need 20 milliseconds to get the data and the measurement back. If you want to measure, like we have a robot with 8 sonars around it, so the whole measurement of each sonar in each direction means that you need to wait like, in fact, 200, but practically a little bit more. So about 400 milliseconds, so half a second for full set of the measurements before we can start to make a second one. So you can imagine that in a certain direction from the certain sonar, we get measurements like 2 times per second, which can be too little for some robotic applications. Okay, because the time is already up, we can finish at that place, and I will continue at the next lecture. But one thing to do for you is try to go with the exercise also for electromagnetic wave and to see of what the results will be. Okay, so thank you. Do you have any questions? Okay, if there are no more questions, so thank you for your attentions and goodbye.